The goal of this video is to give you an intuitive understanding of latitude and longitude coordinates by taking a deep dive into the spherical coordinate system. By the end of this video, you will understand how orbit inclination affects ground track plots, and in future videos, I'll be going deep into the relationship of all the orbital elements with ground tracks. And if you'd like to add your sitting to the ground tracks for future videos, go ahead and leave a comment of where you're watching from. So this is a 30-second video in this series, and I'm going to be going over lat-long coordinates. So as I've gone over in the previous videos, this is the whole procedure of how to turn your Earth center inertial frame position vectors into lat-long coordinates, where you propagate your orbit in the inertial frame, then you rotate all of your position vectors to the Earth-centered Earth-fixed frame, and then from there you convert those rectangular coordinates into spherical coordinates. In this video, I'm going to be focusing on step 3 because it's really important to intuitively understand what's going on with spherical coordinates and how they're defined with respect to the Earth. So spherical coordinates, they're just another coordinate system to represent points in 3D space. The most common you see out there obviously is X, Y, Z, but there's many more systems that exist and they're all equally valid and can be useful in different situations. So there's coordinates like spherical, cylindrical, triangular, polar. There's a lot of things you can do. So basically, if you focus on the diagram on the right, I just drew up a little sketch of how you define the spherical coordinate system in this context. There's a few different ways to do it, but this is the one that is most applicable to how the Earth is defined basically for lat-long coordinates. So you start with a point here. This could be your satellite in your orbit, and you start from the origin to that point. So that's your position vector. That is the position vector. So the magnitude of it, so if you take the magnitude of the position vector, that's the first coordinate in the system is the R coordinate. So it's just the magnitude of that. And then the next two are the latitude and longitude, which some people define the phi and the theta opposite. It doesn't really matter just as long as you understand what's going on. So we'll get to the longitude first. So the longitude is the angle between the position vector projection on the xy plane and the x-axis. Now all that means is that you have your position vector and you just project it down to this xy plane right here. So that vector now looks like this, pointing from the origin to this point in the xy plane. And then the angle that that makes from the x-axis, that is your longitude. That's theta right there. And then the latitude is the angle between the xy plane and the position vector. So you have the xy plane and you have your position vector, and it's just that angle right there, basically how far it's inclined from that xy plane. That is the latitude. Now there's also another way that is commonly defined for the spherical coordinates latitude is actually the angle from the z-axis to the position vector. Both of them are valid. You just have to understand and make sure you know which one you're talking about. But in this case, it's defined as this way because that's the way that it was defined for the Earth, and that's how kind of the lat-long coordinates work for the Earth. So in this diagram here on the left, you can see that we just have some orbit, and then at one particular time it's over here just south of India. So in that case, if you look at the angle, the longitude between the x-axis of the Earth-centered Earth-fixed frame, which is the coordinate system we're looking at, if you take that angle, rotate it all the way over here, that's going to give you some value. And then it is a little bit south of the equator, which is defined as the xy plane, so it's going to have some negative latitude value, and that's kind of how it's defined. And here is just an example of two orbits, two low Earth orbits that I just wrote up real quick. They're 400-kilometer orbits. And one of the white one is at 40 degrees of inclination, and the orange one is at 90 degrees of inclination. And inclination is one of the easiest and most intuitive of the orbital elements to understand in ground tracks, and it's pretty easy to tell because you can tell the inclination of the orbit by how high. So basically, the max of the latitude is going to be what the inclination of the orbit is. So in this white case, you can see that just at the top, it reaches the line of latitude equals 40 degrees. And then at the bottom, it reaches a line of negative 40 degrees. So you know that this orbit has a 40-degree inclination. Whereas for a polar orbit, which has an inclination of 90 degrees, first of all, you can tell because it's coming straight down through the Earth. And you know that its max is at 90 degrees and its min is at negative 90 degrees. So that's one way that you can tell from a ground track plot what the inclination of an orbit is. And the step 2 of the how to transform your ECI position vectors into lat long is to rotate them into the Earth-centered Earth fixed frame. And I'm going to go a little bit deeper into this in the next video. But basically what you get from the spice.px form function is this R ECI to ECEF rotation matrix. Now, I'm not going to be going deep into rotation matrices. That's a whole study of its own, but I'll put a link in the description of some good sources because there's a lot of really good ones out there. So basically what you're going to do is you're going to get this rotation matrix from SPICE. This XECI position vector, you already have this from propagating your orbit in the inertial frame. So this is how you calculate your vector in the Earth-centered Earth fixed frame. And again, I'll go deeper into this in the next video. So that's pretty much it for this video. Make sure you give me a like to help me out with YouTube algorithm if you like the video. And here's a sneak peek to the next video where I'm going to be going over how to calculate the lat long coordinates in Python. So this is basically what my inert to lat long function looks like. And again, I'll be going deeper into it in the next video. So yep, that's it for this one. Let me know if you have any questions in the comments, and thank you for watching.